Hello everyone, I am Ekansh Singh and we'll be presenting our IC272 Data Science Street project on Tarzan the Wonder Driver. My teammates are Samvadan Salgotra, Udayveer Baljit Vark, Taraksh Sambar, Aditya Rohela and Partha Vivedi. The problem statement of our project states that we have to develop a platform which could be either web or Android that will process a video taken from the driver's view and will tell most of the objects, that is the traffic signs along with the meanings, the approximate speed of the car, the landscape and the lane of the car.
Hello guys, I'm Samvedan Silgotra and let's look at the object detection part of the model. For object detection, we actually use YOLO algorithm, which is one of the most popular algorithms for real-time detection of any object present in the image. So let's get to the detailed look at the YOLO. We'll get into the detailed implementation of the YOLO algorithm. So what are the basic techniques used in YOLO? We actually use three basic techniques in YOLO. YOLO first divides the whole image into subblocks, then it performs bounding box regression, and then it has a technique called intersection over union to check its correctness. We'll look at these parts individually in much more detail. So let's first look at division into subblocks. Here, the YOLO algorithm divides the image into subblocks into an S cross S grid, where each cell is analyzed by the YOLO algorithm again. In each cell, the YOLO algorithm tries to detect the object. Now, coming to bounding box regression, the first question is how does it even detect the bounding box? So YOLO uses k-means clustering. The k-means clustering is the main method by which YOLO detects the bounding box. But the question is, what is the distance metric here? Earlier YOLO models actually used Euclidean distance to find the bounding boxes. But now the YOLO algorithm uses IOU, which is intersection over union, as the distance metric. After having found the center of the bound boxes, we have anchors. We have these anchors which are of fixed lengths, and we kind of perform bounding box regression to change their lengths and get different sized anchors. Now coming to the third part, which is intersection over union. What happens in this thing is intersection over union gives us how correct our prediction was. So we know the ground truth. Let's say green box was the ground truth and it shows us the actual position of the object. We have this prediction box, which is the red box. What IOU calculates is it actually calculates the area of the overlap, area of the intersection of these two boxes divided by the area of union. It gives us this ratio. Now, if this ratio is like of significant value, for example, IOU is greater than 0.5, we take that to be as the confidence interval of this prediction. Else, we discard it. Thus, IOU forms kind of a metric of seeing how good our observation was. Now, combining all these techniques, performing bounding box regression, then also like dividing the images into parts, then performing IOU on the image, we get the final output, we get the detection of every image. Now, let's look at the architecture of YOLO v5. YOLO v5 has many layers inbuilt in it. So, what YOLO basically does is it actually reduces the size of the image, and while reducing the size of the image, it has convolutional layers in it, which map out the features. So, at every stage, every reduction of size, we map out different features of the image, and for mapping out those different features of the image, we actually use k-means, which uses IOU as the distance metric. With all these features mapped out, it performs the object detection and gives us the final result. Now, why only YOLO v5? We could have used YOLO v3, YOLO v4, or any algorithm, but the problem was the dataset which was given to us was very specific. It had images of various aspect ratios. YOLO v5 provides us with the ability to fix anchor boxes not of specific aspect ratios. Thus, it worked better for our dataset. Now, Tarak Sambar will explain the implementation.
So hello guys, I'm Taraksh and this is our implementation for YOLO for general object detection and traffic sign detection. So for general object detection, we use the pre-trained YOLO on COCO dataset, and for traffic sign detection, we use transfer learning on the GTS-RB dataset. Firstly, we created the annotations for the GTS-RB dataset with the help of the CSV provided. Uh, the CSV already had the details of the bounding boxes and their coordinates. So we just created the annotation files in the YOLO format. This is the metadata for the dataset. We performed analysis on the data and we found out that the classes were not balanced. So we balanced the classes. We created a YML file for our YOLO, and this created all the names for our classes. We split the dataset into train and test files. Uh, then we trained the dataset for 100 epochs, and then we stored our weights and took the best weights. These were the training results. As you can see, the validation loss also fell as the number of epochs increased. So now Aditya Rohela will take over for landscape detection.
Hi, I'm Aditya Rohila, and the next part of our project is landscape classification. So we are given a data set of about 25,000 images, which had the following six classes: buildings, forests, mountains, glaciers, street, and sea. So we used a convolutional neural network. So it is like a neuron, but instead of neurons, it has filters, which is used to extract features from the images. Here we used max pooling in order which analyzes the info and puts it into multiple channels to increase the resolution. In the end, we also use some dropout layers, which is used to prevent overfitting. We used a softmax function, which is used for multi-class classification. In the end, we compiled our model with the following laws and optimizers.
Hi guys, I'm Uday, so I'll be explaining speed detection. Here we read the input video and separate it by frames and store them in a different directory. In pre-processing, we read all the frames 2 by 2, resize them to 0.5 of the original size, calculate the optical flow between two frames, slice the output into 8 by 6 matrix and flatten it into 1 into 48 array. If there are n frames, the output feature .txt would be of size n cross 48 matrix. While training, we read in the feature that was output from the preprocessed function and train it with our artificial neural network. The output would be a file named model.h5. These were the functions used to perform the task.
Hey, this is Ikansh Singh, and I'll be explaining the lane detection model used in the project. The input video in this model is according to the driver's view, and the output video of the model would highlight the lane in which the car is driving. The lane detection model involves six basic steps. Step 1 would be reading the video and converting it into frames. Step 2 would be the grayscale transformation of these frames. Step 3 would be adding Gaussian blur noise. Step 4 would be using canny edge detection to detect the edges. Step 5 would be masking a region of interest. Step 6 will be using Ho line detectors to extract these features. Step 1 Reading video and converting to frames. With the help of the video capture function of the OpenCV library, we can easily load any video or image sequence in our Python script and convert it into subsequent frames or images. Step 2 Grayscale transformation. Every image contains three channels R, G, B, with ranging values from 0 to 255. Using grayscale, we can convert it into one channel and hence reduce the computational time of the model very largely. This is the required functions and code snippets from our project. Step 3 Gaussian blur. Adding Gaussian noise to an image is useful in smoothing in the interpolation between the pixels. The Gaussian blur function contains kernel image, which typically is a 5 cross 5 matrix, but can vary according to the model. This 5 cross 5 matrix contains values from the normal distribution and is used on every pixel to smooth out the gradient. Higher the kernel, the more blurred the outcome image will be. Step 4 Canny edge detection. Edge detection works on the idea of identification of points in the digital image at which the image brightness changes sharply. These points at which the image brightness changes sharply are organized into a set of curved line segments termed as edges. Canny edge detection offers this way to detect the boundaries of an image using the gradients. These are the required code, functions, and snippets from our project. Step 5 Region of interest. When we perform canny edge detection on the frames, we obtain many redundant edges which are not useful for the model, and hence we use masking a region of interest to extract those lines or edges which are useful. The region of interest basically is a trapezium, in which the black region consists of binary 0 and the white region consists of binary 1. We use the binary operator AND between the canny edge detected image and the region of interest so that the pixel regions lying outside the region of interest become 0 and inside the region of interest are obtained as seen in this figure highlighted here. Step 6 would be using hoof line detectors to extract these features. After we obtain the region of interest, we can use host space, which is basically when a line is represented in the form y is equal to mx plus b, the space consisting of b cross m, that is the constant at which the line cuts the y-axis, and the slope is the host space. And using that, we can extract these edges and superimpose them on the images to obtain the lane detected. These are the required code, functions, and snippets used in our project.
Hi, I'm Aditya Rohela.
And I'm Parth Dwivedi.
So we have together worked on the website part of our model. We have used Flask to integrate the front end with our Python.
So Flask is basically a framework using which we can work with Python. And as regards the front end part, we have just used plain HTML.
So we have first created an object of Flask, and when we have defined its parameters, then we have defined the route parameters such that uh, just after its local host and our port number, just if we write, it will lead us to this upload form, which will show the particular template of upload.html. Then the video that we will submit will be saved to this particular file path, which will then be used by our model to do its computations. This will be the looks of our site, and here we will choose our file and upload it.
So this is the code snippet which will deal with the output. So first of all, as we can see, the port is 7000. So our local host will be port number 7000. The entry point will be defined by this snippet. So here we'll enter the code and we'll just run this app. So on running this app, we'll use the function display video. So this video will fetch the output from the model, and we'll just display this video on our HTML page, and all this will be done using this function here. So this is all about the output.
Okay, so let's look at how we can finally use the model. The first method is you could download the whole project in your local drive, and while you're in the local drive, you run this command here with the source as the path to your input file and the type of the analysis being set to 1. The other method which you could use is you could host the website locally, upload the video there, then after the analysis is done, the video will be automatically downloaded. Okay, so I'm Samvedin and I'll be telling you about the integration of all the models we created throughout this DS3 project. The first model was the custom trained YOLO. We actually saved all the different models we created throughout this project, and then while integrating, we loaded the different models needed for the final output. Here, I developed the code, and in this code, it actually takes the video, loads it frame by frame, and applies all the different models and combines all the predictions and outputs the video, writes it to a video. This is the main parser which actually takes the input path for the file to be on which the prediction is to be made. Okay, so let's look at how we can finally use the model. The first method is you could download the whole project in your local drive, and while you're in the local drive, you run this command here with the source as the path to your input file and the type of the analysis being set to 1. The other method which you could use is you could host the website locally, upload the video there, then after the analysis is done, the video will be automatically downloaded.
So winding up our presentation, these were the contributions made from the team. Ekant Singh worked on lane detection, Samvedan Salgotra worked on YOLO traffic sign and landscape classification. I worked on speed detection, Taraksh worked on YOLO and speed detection, Aditya worked on landscape detection and website, Path worked on website development. So far, this is what we have learned from the project. Object classification techniques that were used in YOLO, transfer learning that were used in YOLO, neural networks that were used in YOLO, landscape detection and speed detection, image preprocessing, edge detection algorithms, and feature extraction were used in lane detection, website development, practical hands-on usage of OpenCV, TensorFlow, and PyTorch framework, integration of models.
Okay, so let's go through an example here. We have the street being classified here as the landscape. We also have the speed being predicted in the left corner. We have the lane being detected. It's kind of highlighted red here. The traffic signs are also being classified. For example, this traffic sign is being classified. We have the objects being classified. Here we have the car and truck. So this was all for the example.